Welcome guys. So I hope you guys subscribe to my channel. Yeah, so this video is the final video about the series in the mathematics analysis video. So we already talked a lot. So next time we talk about the absolute convergence and summation by part. Yeah, so in this video we talk about the manipulation of the series and the rearrangement. Hope you guys subscribe to my channel. Okay. Yeah, so in the first section is the addition and the multiplication of the series. Or the sequence. Yeah, so basically just follow the routine. Okay, so suppose you get an is A, summation an is A, summation Bn is B, right? And obviously summation an plus Bn is A plus B. Yeah, this is trivial. And also summation Cn will be Ca. Okay, so yeah, you can prove these two. So yeah, trivial. I don't want to prove. Okay. And the next, yeah, you can define so how about a product then? It's product then. So let's say you get Cn n from 1 to infinity, also another sequence Bn, B from 1 to unity. And let's define a Cn to be the product of it, right? So it's the Cauchy product AK Bn minus K, K from 0 to n. So this Cn is defined to be this definition. So this Cn is defined to be the sum of, sorry, the product of these two sequences. So given any two sequences, you can construct another sequence. Basically, it's just defined to be this. And I think this is very easy to see, right? If you view this as polynomial and you, yeah, okay. Okay, so the definition is basically multiplied by this. So if you take A and Cn, B and Zn, right? You take from n to 0 to infinity times 2. If you want to write it as Cn, Zn from 0 to infinity, then easy to check that this Cn satisfies this. Okay. Okay, so yeah, so the problem is that let's first see an example to make sure to let you guys understand the complication come from. Okay. Suppose so you see suppose I define an to be this k is partial sum k to 0 to n, and the bn to be bk around 0 to n, and the cn to be small ck. For small ck is what we define k from 0 to n. So let's say an converges to A, Bn converges to B. What about Cn? What about? Okay, so the problem is that we don't have large Cn become An times Bn, right? So it's not obviously that, I mean, if I tell you that C will converge to A times B, which is not clear. Okay, so let's see an example, right? So let's see, I take this original AK to be minus 1k square k plus 1. So our our original AC, this A will be 1 minus 1 over square root 2, 1 minus square root 3, 1 minus square root of 4. Okay. So by the previously telescoping theorem, this guy converge. Okay, and you can try to compute this small Cn 0 of infinity. So the first guy is 1, right? The second guy is the product, the sum of it. So you get this. The third guy is this guy times 3, right? Because this is all the same. So you just, oh, by the way, so this is, suppose you pick these two are all the same sequence, and then you try to compute this, and then you can compute keep going. Okay. Oh, sorry, I'm still sorry. It's square root of 2. There is minus 1 over square root of 4 plus 1 square root of 3 square root of 2 square root of 2 square root of 3 1 minus square root of 4. Keep going. Okay. Okay, so you can prove that so obviously Cn will be k from 0 to n minus 1 to n, 1 divided by square root of n plus n minus k plus 1, k plus 1. Okay, so you can check this, and then you can compute this, right? So this is not difficult. N minus k plus 1, which is n plus 1 square minus n minus 2 minus k square, right? So So now Cn will be greater or equal to, right? If you take absolute value, yeah, so this guy will less or equal to this, right? Because this is square. So this Cn absolute value will larger or equal to k from 0 to n, 2n plus 1, right? Because and n plus 2, right? So you just put in this and then you flip. Okay, so your Cn will greater or equal to this. Sorry, should be 2, right? Should be equal. This is the, and then you count the n term, right? So it should be greater or equal to, it should be this will equal to n plus 1, n plus 2, because there are n plus 1 term. Okay, so now you see if n goes to infinity, right? So this guy becomes 2, which means that Cn will not converge. Cn will not converge, right? For each term, right? So each term, each small Cn is not converge as n goes to infinity. Okay. So now the problem is that even though the AB converge, but the Cn, the product of the two sequences not necessarily converge. Okay, so this is the theorem that we have to prove, called the Merten's theorem. Okay, so Merten's theorem says that suppose the following is true: an converge absolute value, an converge absolutely, and then let's say an converge to A, and also Bn converge to B. Yeah, so A, B, and all of it can converge, and then that's defined as small cn to be the A, K, Bn minus K, K from 0 to n, small cn, then summation n from 0 to infinity will equals to AB. So this is the amazing results that the product of sequence actually the product of AB. It's not necessarily obvious. Okay, so I think this is the merits of this video. We just prove it. Okay, maybe I use small. Yeah, okay, shit. I use small cn. Okay. Oh, I use small cn, right? And the large cn to be a small cn. Oh, wait, maybe I use tilde cn to make sure. I'm not confused myself. So I use tilde c n to be the each term, and the large cn to be or no tilde cn to be the partial, to be a partial sum. Okay. That only proof. Okay, so yeah, so let's see what's large cn. Right, so large cn can be written as a0 b0, right, plus a0 b1 a1 b0, and second, and right, so keep going, which is the second term, the up to a0 bn a1 bn minus 1 to an b0, right? Okay, so this term, the first, let's define the large bn, right, to be the partial sum of bn, so k from 0 to n. So the first term is a0 bn. Let's see, right? So I can take all the a0, right? I take all a0, I get a0 bn, and I take a1, I get a1 bn minus 1, I get an b0, right? So large b0 is a small b0, right, by this partial sum. Okay, so this is a0 plus b plus beta n. Okay, so let's define beta n. So beta n is bn minus b. Okay. So right, so this beta plus beta, because beta, right, so yeah, so this a0, let's see what the hell is going on. Yeah, right, so bn, right, bn is defined to be beta n plus b, right? So bn beta b plus beta, b is converge, b plus beta n, right? By because large bn is beta n plus b. Okay, and the a1 will be a1 b plus beta n minus 1 up to an b plus beta 0, right? beta 0 should be 0. Okay, so from this, let's make a so okay, so let's take all the b, large b out, right? So okay, we got a0, a1, an. So this is an, right? So partial an is the partial sum of this small a plus a0 beta n, a1 beta n minus 1, a n beta 0. Okay, so yeah, tricky proof. Okay, so let's define a gamma n, right? So obviously define the gamma n should be defined to be this, right? Right, so gamma n will be a0 bn beta n a1 beta n minus 1 to a n beta 0. Okay. Okay, so so we hope to show this large Cn converge to AB, right? So and we know that An times B converge to AB by our definition, right? So that's if we take n to infinity, that this is already B times A. So the rest is to show what? Show this gamma n goes to 0. Because this guy, right? This guy already converged to B times A, so we only need to show this guy converge to 0. Okay, so somebody need to prove the gamma n goes to 0 and goes to infinity, right? So it's just to bound the gamma n. So let's try to bound gamma n, right? So gamma n can be bounded by this. So we can be bounded by two terms. So let's remember that this small beta n, right, goes to 0 because b goes to beta n, right? So if small beta n goes to 0, that means one can choose n, right? I can pick out large n such that beta n less or equal to epsilon when n greater or equal to n. Okay, so gamma n is less or equal to beta 0 a n beta n a n minus n plus beta n plus 1 a small n minus large n minus 1 to beta n a0. Okay, so this is just the same, right? Just pick up with two term. Okay, so so this term, right? So this term can be controlled because my large n, my small n is greater or equal to large n. So this term is bounded by epsilon alpha, right? So what is this alpha? Let's define alpha to be a summation of a n absolute value n from 0 to infinity, because I assume that the an is absolute converge, so this guy converge. So this is bounded by epsilon alpha. Okay, so that means we already bound this term. Okay, so we can fix n and let n goes to infinity. Okay, so yeah, when n goes to infinity, right? When n goes to infinity, then this term is all any an minus 1 and up to a small n minus large n, right? But because summation an converge, right? So you know that an converges 0 as n increasing. So which tell you that these terms will goes to 0, right? And this term is bounded by epsilon, right? So finally, obviously that you can get, if you take a limit soup, you get your gamma n less or equal to epsilon alpha, right? Because this remaining term it already goes to 0 as n goes to infinity. And then this epsilon can control, right? So you can make larger and large. You can make n large enough for any epsilon, right? So which tell you that gamma n goes to 0 as n goes to infinity. So you first, so let me just go back to illustrate the idea. So you first, you use this alpha to control this term, and then you fix n and let small n goes to infinity. So you use the conversion of an to control the first term, to make the first term arbitrarily small. Then you use the conversion of the b to make this epsilon as small, arbitrarily small. So so this limit sub gamma should less or equal to any epsilon, which you get 0. Okay. Okay. So from the previous results, we get theorem. Cn, an, b, and Cn. If all your an, b, and Cn converge absolutely, so that means these three guys converge, then C equals to AB. sorry, this Cn is basically bad idea. So Cn tilde, which Cn tilde is defined to be a0 plus bn a and b0. Okay, so this theorem just tell you that if you have two absolute convergent series, you have two absolute convergent sequence, and then you can define a third, which you define each term is just look like the polynomial multiplication. Then finally, this large C will convert to A times B. Okay, so this is an interesting topic, but yeah, we proved this Merten's theorem. Okay, so finally, let's prove the famous results called the rearrangement. Yeah, so this is I think it's the most astonishing result in a series called the rearrangement. Yeah, so which tell you that once you rearrangement a convergent sequence, sometimes then you will make this sequence diverge, or sometimes you arrange some divergent sequence, then you will make it converge. So which tell you that the real number is the behavior of real number is very weird. Okay. Yeah, so let's define a rearrangement. So define a rearrangement is very easy. So let's say Kn, right, from 1 to 2. So for each number, you give another Kn, right? And such that every positive integer appear once and only once. So that means you get K1. So you can K1, K3, K2, K3, K4, such that so there is a set. So this is a set such that this K so such that every integer, every non-negative integer only appear once. I should say it must appear once. So basically, this is a rearrangement, right? So for example, if you start, so original one is a rearrangement, or I can change these two, right? Or I can change these two, and keep going. So basically, you can use all the original series, but you cannot add them or delete them. You need to use all of it, and but the order can be different. Yeah. So this is the definition. Okay. Yeah. So I can define an prime to be AKN. Right. Yeah. So this new an prime is called the rearrangement of an. So this one can converge of an prime and an. Right. So obviously that if an is if only a finite number, then this still be right. They should be the same. Okay, but well, we can start from some interesting example, which is so weird. Okay, so we start from this is the textbook results. Yeah, we know that this is converted to log 2. Okay. Okay, so let's do some rearrangement to make it 1 plus 1 over 3. So I take this guy and the minus 1/2 plus 1 over 5, 1 over 7 minus 1 over 4 plus 1 over 9 plus 1 over 11 minus 1 over 6. Right, so I add two terms and the minus 1 negative, add the 2 positive, 1 negative, and keep going. Okay. And let's assume that yeah, maybe let me just default this to be S. Okay, and I want to show that this sequence do not converge to S. Okay, so this is our, so that means we use a still, we change a little bit, but this original do not converge to this. Okay, how to prove it? So let's see, oh yeah, this is S. So let's see from original one, S, right? So S is less than, because this is minus, right? So S is less than the first 3 term, right? So S is less than this. Okay. Right. But how about this? So what is this, right? So now you see you can take this. Okay. Give me one sentence. Okay. yeah. So let's see. Yeah. So let's see this. Let's call it S3 prime, and these 6 are called X6 prime, and these are called X9 prime. Yeah. So let's see. So by this construction, you know that S3 prime, right? So S3 prime is less than X6 prime because S3 prime is positive, and then you add another term, right? So S3 X9 prime. Okay. But you notice the thing, right? You notice the thing that the S3 prime is what? S3 prime is just 5/6, right? So by definition, if you take limit sup n goes to infinity, this ends n prime will definitely greater than S3 prime, which is 5/6, right? But original S is less than 5/6. So which proves that the converge of the second series. So this is right. This is 2C for second series, the first one series. Their converge results will definitely be different, right? Because S will less than 5/6, but this S prime will larger than 5/6. So 2 will not the same as 1. Weird. Okay. So that means what? That means a change or I say it means that rearrange will make results different. Will make conversion results different. But yeah, so this is just some systematic, some example, one example, right? But there is a theorem that what Riemann prove about rearrangement. So theorem, which is the key we have to prove. So suppose you have n which is a real and a converge, but not absolute, but not absolutely. So this means that the absolute this guy will not converge, will become infinity, but this guy converge. Then you can rearrangement, right? There exists a rearrangement n prime such that let's say the partial sum of rearrangement is called Sn, such that the inf of Sn prime is alpha, limit n goes to infinity, limit sup of Sn prime is beta. What for any beta, for any alpha and beta, that's equal to infinity. Enough. So basically, you pick up any true number, you can find you can rearrange a non-absolute converge sequence to make its limit inf and limit sup match one match beta, one match alpha. So basically, this theorem just say that you can, if you give me any number, then I can make this sequence converge to any number you want. So whether it diverge or whether it converge, but if diverge, then it's fine. I can pick up the diverge. If you give me another any number, then I can rearrange it to make it convert to that number. So this is the Riemann's theorem. So basically, what I'm saying is that the rearrangement can give everything, can give you any number, can make the sequence converge to any number. Okay. Okay, so this is the theorem, that the final theorem we want to prove. And also we will prove that we will prove another is that if the sequence converge absolutely, then the rearrangement will not give difference. Okay, so proof. So let's say define let's say Pn to be An plus An absolute value divided by 2, and the Qn will be An minus An divided by 2. Okay. So which just tell you that the Pn minus Qn is An, right? And Pn plus Qn is An. Right. So from these two, we know that one since summation of this guy converge, this guy diverge, right? So the summation Pn and Qn both diverge. Okay, so that means all of this guy will not converge to anything. Okay, so also notice that if An and An converge, right? If all of these converge, then Pn Qn converge. Right, will converge. Okay. Okay, so this is just some notation. Okay. So let's let P1, P2, P3 denote the non-negative term of AN. So non-negative term of AN. And summation non-negative of AN. And yeah, and Q1, Q2 to be the negative term in AN. So I just collect us. I just pick up all the positive term and all the negative term, and collect it as P1, P2, P3, and the negative then Q1, Q2, Q3. Okay, and yeah, by definition, right? If you see that so now you see that this Pn and Qn are basically this large P1 and P2 and this summation Pn. So the summation this and the summation Qn, right? So they differ from original. They differ from summation Pn and Qn, right? So this Pn, if it's positive, then become Pn. If it become Pn will become non-zero. If it's negative, then Qn become non-zero, right? So which tells us this sigma Pn and Qn differ from sigma Pn and Qn only by zero term, right? So basically, which tells you that the summation of Pn and Qn. So basically, you pick up all the positive part or negative part, then it must be diverge, right? Because they are close to this. Okay, so now we hope to construct a sequence satisfy you given any alpha beta, and I want to rearrange it into alpha and beta. Okay. Yeah, this proof probably the most difficult proof. Right, so let's construct. So let's say we pick out another two sequence. Another two arrangement. Another two sequence of Mn and Kn. Such that P1 up to Pm1 minus Q1 minus minus 2QK1 plus Pm1 plus 1 plus Pm2 plus Pm1 plus 1, right? Up to Pm2. Right, so this is P, right? And minus QK1 plus 1 up to QKN, K2, right? I hope you guys see a trick, right? So we hope to construct this sequence such that so this sequence is just rearrange of A, right? Satisfied our results, satisfy our goal. Right, so this is we hope to construct. Okay, so now how to do this? How to do this? Okay, so oh, he doesn't have any page. Yeah, let me just add some page. Yeah, no, let's keep going. Okay, so let's see. So I pick M1 and K1 such that M1 and K1 are smallest integer such that P1 up to Pm1 greater than beta 1. Okay, so notice that this guy diverge, right? So however I can make it greater than beta 1 because it's all positive. And for this guy, I use another K1 such that which this guy less than alpha 1, right? Okay, so what's alpha 1 and beta 1? So I pick up alpha n, which converge to alpha, beta, and converge to beta. Okay, and such that we always have alpha n less than beta n and beta 1 greater than 0, right? So remember that our goal is to find alpha and beta. Our goal is to construct a sequence which limit inf is alpha, limit is beta, right? So I pick out sequence a alpha n approach to alpha and the beta and convert approach to beta, but such that alpha n less than beta and the beta 1 greater than 0. Okay. So I can pick out these two, right? Because this is all positive, then it diverges, so it must go infinity. I can find the smallest M1 such that it's satisfied. And I can make this also. I can make some guy which is large in negative enough so to cancel the first one and approach alpha 1. Okay, and I keep doing the same thing, right? And I get a M2, I let M2 and K2 such that the smallest one, such that this guy minus Q1 minus QK1, right, plus PM1 plus 1 plus PM2 larger than beta 2, right? Because this guy is negative, right? But I can find always, because it's diverge and it goes to infinity, so I can find I can always find lots of P, such that P can be arbitrarily large, right? So make this greater than beta 2, right? And now you guys do the same thing. Minus this, so this term pick up, put in here, and the minus Q K1 plus 1 minus QK2, right? Less than alpha 2. Okay, so now you guys see a trick. I can keep going, right? Yeah, so so let's define, let's keep going, and yeah, so now I guess you guys see a trick. So this M1 and K1 are smallest integer such that this greater than beta 1, and then this minus P minus Q part less than alpha 1, and M2 is this part greater than beta 1, and K2 is the alpha 2, right? So this, remember that this M1 and K1 and M2 and K2 are the smallest integer such that this happens. Okay, so let's define xn and yn, right? So let's define this. So this guy is x1, this guy is x2, y1, and this guy is x2, this guy is y2, right? So by definition, this xn, which is the small, so remember this xn. So remember that this xn, the last term of this xn2 will be the min and the pmn, right? Which from positive term by n, and the yn will be the final term is negative minus qk2. So this pn is smallest one such that make xn to greater than beta n, right? So which tell you that xn minus beta n will less or equals to pmn, right? Because this is the smallest one. So that means before you add this one, it do not greater than beta n. Once you add this pmn, then it starts greater than p beta n. So which makes you that xn minus beta n is less or equal to pmn. So same reason, yn minus alpha n will less or equal to qkn, right? But we already proved what? Yeah, so we already proved that the pn converges to 0 and the qn converges to 0. Why? Because sigma n converge. So whenever it's a positive part or whenever it's negative part, then the largest n enough converge. Okay. So which proves that your xn will approach to beta and the yn will approach to alpha, right? So which make you that, so it tell you that there exists a rearrangement such that this rearrangement, just do this, and one converge beta, one converge alpha. Okay. So which prove our results. Yeah. Okay. Very nice. Okay. So final theorem. So if sigma n converge absolutely, then rearrange, then every rearrangement converge. To the same sum. Okay, so let's suppose sigma n prime is a rearrangement, right? And the partial sum is Sn prime. So let's say k from 0 to n. So for all epsilon greater than 0, right, the partial sum converge, right? So this is stupid because for epsilon greater than 0, the partial sum I from 1 to k, let's say I from 1 to m, less or equal to epsilon, right? So if you take absolute value, less or equal to epsilon. So now, if you only see the Cauchy condition, then you only take the partial sum, right? But this is all finite, so rearrangement do not make a difference, and then you take absolute value. So this guy will not make any difference, right? Because this is there's the absolute value, right? So let's maybe let me do a little bit slower to make you understand. Okay, so we know that summation n converge, right? So it means for epsilon greater than 0, for any m and n larger than large n, you have this. Right? You have this. Right? You have this. Okay, so now let's say you have a rearrangement. You have a rearrangement, right? So let me just choose P such that 1 to 2 to n are all contained in set K1, K2 up to Kp. Okay. So this is the rearrangement, right? So suppose you rearrange some K1, K2, Kp. And I can choose P such that 1 to 2 to n are all contained in the set. Okay. So that means if n greater than P, then then A1, A2, AN, right, will cancel the difference. Sn minus Sn prime, right? Okay, so which just tell you that your Sn minus Sn prime, right, will less or equal to epsilon. Okay, so now for n, right, for large enough n, so which make Sn approach to Sn prime. Okay, yeah, so yeah, I think this is a proof. Okay, so see you guys next videos. So next video we start to talk about continuity.